Okay, so let me do these questions. I've been wanting to do or redo these elastic collision questions for I think about a year, at least more than a semester, because I think about a year ago I learned a new way. Well, I guess it's not actually new, but it was new to me. I learned it from ChatGPT. So it's a quicker way to do elastic collisions. Now, conceptually, it is. I do think it is more complicated than just a simple application of conservation of momentum and energy. That's conceptually a lot easier. This particular formula that can be derived for one-dimensional elastic collision, it makes math a lot easier. So let me present this second version of all the elastic collision questions you have in the homework so far. And you have seen me approach this with all the complicated algebra. Let me see if I can group them all and just do them all together. And because the algebra is going to be so much easier with this particular approach. So I'm going to go to the lecture where I go over all this. It's in lecture 14. What's called the relative velocity relationship. If you're on a Google search, that's how you would find it. And I'm just gonna basically look up the formula here. In this lecture, I go through the whole derivation of that. Don't need that. You can watch it. You can go watch it if you want to see the derivation. At the moment, all I'm interested in is this. The relative velocity formula as derived. The primed quantity there means it's the after collision picture. I'll use the labels of the initial and final. So relative velocity relationship. And I want to make it clear that people don't abuse, misuse, use it in context where it doesn't apply. So let me clearly say it's for elastic 1D collision only. And what's derived here is, let me write it down. So you are looking at two objects colliding. One of them is object 1 and the other is object 2. And it's a general relationship. One doesn't have to be at rest or anything. V1, and their masses can be different too, even though this formula doesn't have any masses in it. V1 initial plus V1 final is equal to V2 initial plus V2 final. And as you will see, when you see the derivation that's done in this video, this relationship already contains the information that it's elastic. So when you use this equation, it's kind of physically equivalent to use conservation of kinetic energy. The advantage of using this formula rather than conservation of kinetic energy, which let me just write out. The conservation of kinetic energy says 1/2 m1 v1 squared, initial, plus 1/2 m2 v2 initial squared is equal to 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. This is what conservation of kinetic energy says. The advantage of this expression over this is that this is linear equation. It doesn't involve any squares, so that makes your algebra just so much easier. It's a linear equation. And I kind of talk about in this video what the trade-off, catch of using this formula is. But other than that catch that you will see mentioned in this video, it's equivalent to using conservation of kinetic energy equation. So for the purpose of this problem solving, I'm not going to use conservation of kinetic energy. That's the whole point. You already have my other videos where I do use conservation of kinetic energy to do these elastic collision questions. So using this relative velocity relationship, let me approach these elastic collision questions. Now I do need a second equation to solve for two unknowns that's going to come up eventually. And the second equation that I'll continue to use is conservation of momentum. All these collisions that you will see conserves momentum. So I will say mass 1 times the initial velocity of 1 plus mass 2 initial velocity of 2 is equal to mass 1, the final velocity of 1 plus mass 2 times final velocity of 2. And I'm going to treat these quantities like they are vectors. They can be positive, they can be negative, and the signs will indicate whether it's moving in the positive direction or negative direction. So these two will be the equations I will use for every one of the problems that you will see me do now. There's, I think, 4 questions total. This question counting is 2 because questions 47 and 48 combined. So it says, in an elastic collision, a 440 kilogram bumper car collides directly from behind with a second identical bumper car that is traveling in the same direction. Initial speed of the leading car is that, trailing car is that. Assuming that the mass of the drivers is much less, okay, ignore the driver. What are their final speeds? So what they are telling us for this part A, they are telling us to assume that M1 is equal to M2 because the bumper cars have the same mass, 440 kilograms, and the driver's mass don't matter. Then masses are the same. That simplifies these two equations, especially equation 2. So from equation 2, what you end up with is canceling all the masses. You have V1 initial plus V2 initial is equal to V1 final plus V2 final. So take this equation, stare at this equation for a bit, then I hope you come up with an answer. Or let me go through the algebra since it's pretty simple. So I got 2 unknowns. The 2 final velocities are unknown. So let me solve. Let me label the leading bumper car as 1 and the trailing car as 2. So I'm gonna eliminate the velocity of the trailing car V2, plug it into my equation 1, and then solve for the final velocity of the leading bumper car. So solving this for the trailing bumper car, V2 final is equal to V1 initial plus V2 initial minus V1 final. And you all see algebra is pretty simple. When I plug this in there, what I end up with is V1 initial plus V1 final is equal to V2 initial, and instead of V2 final, I'm plugging this in. V1 initial plus V2 initial minus V1 final. So V1 final is what I'm trying to solve for. It occurs here and here. And looking at this, I see that I have V1 initial on both sides, so I can cancel them out. Imagine subtracting it from both sides. On the right hand side, I have these 2 terms. So combining them, it becomes 2 V2 initial. And I can imagine moving V1 final over to the left hand side. Combining with this, I get 2 V1 final. So 2's cancel. So V1 final is equal to V2 initial. This is something that you might have guessed intuitively. Intuitively, the leading bumper car now moves faster at 7.5. Basically, their velocities swap. And if it becomes 7.5, then I think you can get directly from this relative velocity relationship that the V2F that we eliminated must be equal to V1 initial. So that this should be 5.2. So this is the easier part of the question. Even using conservation of kinetic energy, could have done it in like less than a minute. Spending a lot more time explaining. So let's do part B, which is a little bit harder. So assuming that the total mass of the car is 20% greater, so now we no longer have that nice thing we had. For part B, this is no longer true. So we have to say leading bumper car, my car number 2. So M2 is 20% greater than that of the trailing bumper car. So it's 1.2 times N1. That way M2 is 20% greater than the mass of the trailing bumper car. Now we have to work out the math to get the final velocities. This time I can simply guess, like the previous one that I could have. Here, I just had to do the algebra. And again, what I'm telling you is that with the help of the relative velocity relationship, this algebra is so much easier than it used to be. So let me first write down a simplified version of equation 2. So I can imagine substituting in for m2. So I'll have m1 in every term. That will cancel out. So simplified version looks like this. v1 initial plus, and what was m2 will become 1.2 times v2 initial is equal to m1, so it cancels out. v1 final plus m2 becomes 1.2 m1, and m1 cancels out. v2 final. So I'm combining this with the relative velocity relationship to solve for my unknowns. Let me go in the same order. So I'll solve for v1 first, the leading bumper car. So this time what I will do is I'm going to solve equation 1 for v2 finals with a view to eliminating it. So v2 final is equal to, move v2 initial over, v1 initial plus v1 final minus v2 initial. So plugging in this into here, I end up with v1 initial plus 1.2 v2 initial is equal to v1 final that I'll hopefully solve for in the end, plus 1.2 times, I should make sure to distribute it in later, v1 initial plus v1 final minus v2 initial. Okay, let's just stare at this for a while, have a plan of what to do. So I need to solve for the v1 final, that's what I want to solve for. So I can imagine combining this and this, remembering the 1.2 here. So doing that will get me 2.2 v1 final. I've taken care of these two terms. All the other terms are known quantities, v1 initial, v2 initial. I should move it over to the other side so that I can simplify it. So let me move this over to the other side. I'm making room. So I have v1 initial plus 1.2 v2 initial, and then moving this over carefully, minus 1.2 v1 initial, and then I already took care of that, so this other term, it's going to be plus 1.2 v2 initial. And I could do more method to simplify this, but let me just be a little bit lazy and just get to this numerical answer as quickly as I can. So for that, all I have to do is divide both sides by 2.2 to get rid of this. Then what I have here will give me the numerical value that I can plug in and get it as a correct answer. So let me do that. I can just put it all into Wolfram alpha. v1 initial was 5.2, the speed of the leading bumper car, plus 1.2 times v2 initial, that was 7.5, minus 1.2 times the v1 initial, 5.2, plus 1.2 times v2 initial, 7.5. These are the like terms that I could have combined. I just decided not to. Divide by 2.2. So I get 7.71. Interesting. Once I have that number, then I can get the speed of the trailing bumper car pretty quickly using the relative velocity relationship again. Or I guess I actually solved for it here. So let me do that. Here I already knew v1 initial and v2 initial, and now I know v1 final. So let me just preserve this as the v1 final that I'll be using. I add to that v1 initial 5.2, and I subtract v2 initial 7.5. So 5.41. And let's see. Oh wait, it says it's incorrect. Wait, what mistake did I make? And that is always a danger of going too fast. M2. Oh, it's not M. Leading bumper car is car 1. So oops. so I made an oopsie here, which is really not that, but 1.2. It should have been here. So I think that means wherever I see 1.2, I changed that to 1 over 1.2, 1 over 1.2, 1 over 1.2, 1 over 1.2, and instead of this being 2.2, it's 1 plus 1 over 1.2. Let's do it that way. So this is 1 plus 1 over 1.2. This is one of the things I like about using Wolfram Alpha. The fix is easier to make because all I have to do is, so let me just go, well, yeah. All I have to do is just change the numbers. I had it before where it was 1.2, I mean, so 1 over 1.2. There are, more sensible way to put in these numbers if I had the 1.2 on the correct side from the start, but this is sort of what I have to do, doing the fix after the fact. 1 plus 1 over 1.2. Okay, so this should give me correct V1 final. It's 7.29. Let's just double check that first before I do more work getting the V2 final. Yeah, okay, that's correct. And let's do the work for the V2 final. So that should be, so add the V1, I think. Yeah, add V1 initial, V2. I mean, sorry, 5.2. And then subtract V2 initial, 7.5. So that should get me, oops, were there, oh, I see. Yeah, they were mismatched parentheses. All right, let's hope. I don't know what I would have said, but let's just get the correct answer. 4.99. So other than that little hiccup with the which one is 20% heavier, algebra is much quicker. So let me do I think I can actually do the other two questions. So that normally, I would have separated them because the algebra would have taken so much longer. So long that I can't really do them in one single video. But let me just go to that other question and do this, much quicker algebra just in one video. So this is the other question. Now the question itself asks about kinetic energies, but this is what I have to say. Once you know the velocities or post-collision velocities of these particles, then kinetic energy is easy to calculate. So that's what I'm going to do first, using these two equations that apply to elastic 1D collisions, particularly the relative velocity relationship that encodes the kinetic energy conservation into a really simplified form. I'm going to find their final velocities first. And once I find their final velocities, then I can figure out, okay, what percentage of kinetic energy is that? So, let me say an alpha particle undergoes an elastic collision with a stationary cold nucleus. Do they give the... Okay, we have the masses of particles, good. Yeah, so let me just copy down those masses and then I don't have to keep them up. So mass of the helium particle is 4.0026. I think this is a unified atomic mass unit. It's some uniform reference number. That's, I think, all we care about. And the mass of the gold particle is 196.9666 U. I probably could have used their mass numbers 4 and 197, and it would have been close. But let's just be precise. So the very first thing to do is for this picture where I have a gold initially at rest. So let me say this is V2 initial, that's 0. There's gonna be a helium that comes in with some velocity, V1 initial, and then they will collide, and after collision, I think the helium will bounce back with V2, with V1 final, and I'll keep it as a kind of signed quantity. So my V1 final will end up being negative. And I'll have gold that's gonna be bouncing forward with the V2 final that's no longer 0. So it asks what percent of the kinetic energy of alpha particle is transferred to the gold nucleus. So ultimately the answer that they are looking for here, it's the ratio of the kinetic energy of the gold after collision over kinetic energy of helium before collision. Or in terms of all the quantities, it's 1/2 mass of gold that I have times V final 2 squared divided by 1/2 mass of the helium times V initial 1 squared. Now I don't technically have a V initial 1, so what I would do is I'm going to get an expression for V2 final in terms of V1 initial, and then I should have enough information to do this calculation with the things that cancel out and all that. So let's so our first goal right now is to solve for V2 final, and that counter intuitively means I'm actually going to solve for V2 initial first, because I'm going to eliminate it from my system of two linear, beautiful linear equations. So let me solve for V2 initial from my V2 initial, sorry. What I'm solving for is V1 final. Yeah. So let me solve for my V1 final. That's the currently unknown, presumably, speed of the helium particle after the collision. So solving for that, out of equation 1, I have V1 final is equal to V2 initial plus V2 final minus V1 initial. Simple. Plug that in into the conservation of momentum equation, then I get M1, let me write it out as mass of the helium particle times, I'll keep V1 initial as it is, plus M2, that's going to be mass of the gold particle. Oh, but V2 initial is 0. So this will be 0, so I'll just, or let me do it properly. V2 initial, which will be 0. So this simplifies my expression somewhat. And I have mass of the helium times, now I use this expression instead of V1 final. So it's a V2 initial, which is 0, plus V2 final, which I'm trying to solve for, minus V1 initial, which hopefully I can express everything in terms of. Plus, I have mass of the gold times the V2 final. Yeah, so I'm still trying to solve for that. So I see that both sides have the, or on the right hand side is where I have this V2 final that I'm trying to solve for. So let me combine the like terms that way. So on the right hand side, it looks like what I'll have is, I have this term and this term. I can imagine collecting the like terms, factoring out V2 final. So it'll be mass of helium plus mass of gold times V2 final. Let's take those terms taken care of. One of the terms was 0, so I really have this term that I have to just move to left. So let me write down the left hand side with this term, move to the left. I have mass of the helium times V1 initial, now plus, that's interesting, well, plus mass of helium times V1 initial. So these are the two exact same terms. So get rid of one, make one of them 2. So it says, let me just move this to make myself a little bit of room. Let me solve for V2 final here, and I think I can wrap up. So V2 final, so dividing both sides by basically the sum of the masses, is 2 mass of the helium times V1 initial divided by the sum of the masses of the helium and the gold. Oh, so I think let me do that substitution here. The writing's gonna be a little bit in the way, but yeah, I'll just do it, suffer through. So saying equals 1/2 canceled out. I have ratio of the masses of gold over helium, and let me square them as I go. So I have 2 squared, 4 times the mass of the helium squared, times the V1 initial squared. It's gonna get cancelled out, but I'll put it in anyway. And then I've divided by those masses squared. Let me just put it on the denominator, just to, I don't know, save room. Sum of the masses squared times, now what's actually on the denominator, I already took care of the mass of the helium. I have a V1 initial squared. So the V1 initial, which we were assuming we knew, we are hoping it would cancel out, it does cancel out. So my final answer is this ratio of masses. So let me plug in this ratio of masses into Wolfram alpha, and let's hope the answer is graded as correct. So I'm going to be putting masses in this way. I'm just going to put in the numerical value of this coefficient, and the unit, U, the atomic mass unit, will just cancel out. I'm just going to trust that will happen. So mass of gold, 196.9636, divided by mass of helium, 4.026. Okay, that's the coefficient up front. I could have done a little bit of simplification with the cancellation, but I only get to cancel one factor of mass of helium, so it didn't seem like a lot of benefit. So 4 times mass of helium, 4.0026 squared, because I chose not to cancel it, divided by the sum of the masses, 196.966 plus 4.0026, and then this thing squared. So that should give me the right answer. Now it seems a little bit large. That makes me worry. Maybe it's right. So the answer they're looking for is percent. This is just the ratio. So for the percent answer, I need to multiply this with 100. So it's a 7.81%. Seems large to me, but maybe it's not. Oh, all right. I guess that's right. I might me remembering saying smaller number might be, I don't know, proton hitting gold, maybe. But yeah. This again. I think it took me like 10 minutes. That's a lot quicker than what using the kinetic energy formulas would have been. So yeah. It's again it's the advantage of the relative velocity relationship that that math is so much easier. You only have to deal with the linear equations. Now the downside of it is, I guess I would have presented as twofold. One, I think conceptually it's a little bit more opaque. Like it's not as clear like what is being conserved. You have to remember for yourself that when you are using this relative velocity relationship, it only holds for elastic collisions in 1D. So that's the situation that you are allowed to use it in. So conceptually it's more opaque, and the other downside is because it's conceptually more opaque, you might make a mistake remembering this formula. I wrote this down in the form that I will remember. I think writing down in this form, I won't ever make a sign errors in remembering this. But most textbooks write it in a different way, and I think the form in which most other textbooks that have this formula, not ours, Giancolli has it, Young and Friedman has it. The way those other textbooks presented, I think it's really easy to make a sign error. So those are the two downsides. But like if you're careful with it, it's like sharp knife. It can be a great tool. Okay, let me go to the third and the last question, and then I'll wrap up this group of questions. All right, that's a long-looking question. It's a question number 98. It helps me with the editing later. So it says derive the equations giving the final speeds for two objects that collide elastically with a mass of the. Okay, you are doing it general. So I guess it's basically this formula. Initial speeds being so let me write down the simplified version of these formulas. So equation 1 simplifies into V1 initial is V0 plus V1 final is that's an unknown, So I think they are calling it V1. So let me just call it V1 is equal to V2 initial. They said it's 0 plus V2 final. That's what they are calling V2. Equation 2 becomes, they have different masses, so I can't cancel masses. It's M1 times V1 initial, which is V0, plus, this will be 0 because V2 initial is 0, so 0 is equal to M1 times V1 final that they are calling V1 plus M2 times V2 final that they are calling V2. So two equations, two unknowns, easy to solve. Let's so this already has a solved for V2. So let's just use that to eliminate V2 from my second equation. Then I have M1 V0 is equal to M1 V1 plus M2, and what I have here, V0 plus V1, kind of combine V0 on the other side. Is that right? I guess that's probably right. V0 on the other side. So it's M1 minus M2. I'm combining them and then factoring out V0 is equal to, on the right hand side I have M1 plus M2 times V1. I think that's right. So V1 has possibility of being negative if it's colliding into an object that's heavier than object 1, then object 1 can bounce backward basically. So I think this is right. Let's double check and see. So M1 minus M2. You can, by the way, also look up these variables from here. So M1 plus M2. That also sometimes helps a little bit because you know what variables the question expects your answer to be in. So yeah, that's correct. That means so V2 you could simplify it, and I do strongly encourage that you give it a try. You can also do this. You can plug this into here and just present it in that unsimplified form, and the homework system will accept it as correct. It won't be too picky about whether it's simplified or not. But I think if you simplify, you will see some. Here, I don't know if it's all that much simpler. Sometimes through simplification, you can gain some physical insight. Here, I'm not sure if you do. So with that, okay, consider your answer carefully. Match the conditions below with what you physically observe. Okay, mass 1 less than M2. Oh, that's what I was saying. It'll bounce backward, and that you can see that from V1 becoming negative. So that's gonna be B. M1 equal to M2. So V1 will become 0. So object 1 just comes to a stop. Comes to a complete stop. Yeah. So that's A. M1 greater than M2, so that's where the V1 is positive, meaning object 1 just continues to move forward just at a slower speed, having transferred some energy into object 2. That should be right. C shouldn't match anything because yeah. Good. So this is the third question. You see how much more quicker this was, even working out these general relationships using relative velocity relationship formula. That's why I want you to do it, because it's a I think it's an approach that for those of you, this makes a conceptual sense. It's a shortcut. It's like a mental method trick. It can speed up your problem solving. For those of you who feel like you know how to do elastic collision, it's just tedious working through conservation of kinetic energy equation. After you know how to do that longer way, this shorter way can help you do it more quickly.